So let us deal with lecture 3 of current electricity. We will be solving some problems based on the formulas and concepts we have learnt in the previous two lectures. Let us begin with the first problem. The storage battery of a car has an EMF of 12 volt. If the internal resistance of the battery is 0.4 ohm, what is the maximum current that can be drawn from the battery? So if we consider this problem, the EMF of the cell is equal to 12 volt and the internal resistance value is mentioned as 0.4 ohm. So if we calculate the maximum current which can be drawn from the battery, it will be when the external resistance is almost negligible. Almost negligible. So if it is so I can write that the maximum value of current is equal to E by small r, and it can be written as 12 upon 0.4, which is equal to 30 ampere. So let us deal with the next problem. A battery of EMF 10 volt and internal resistance 3 ohm is connected to the resistor. If the current in the circuit is 0.5 ampere, what is the resistance of the resistor? What is the terminal voltage of the battery when the circuit is closed? So for this, let us draw a simple circuit which the question is talking about. So there is an external resistor which is connected with a battery of EMF E and internal resistance is small r. And the current that is flowing in the circuit is I. This is the terminal voltage the problem is talking about between the points A and B. So if we consider this problem, it is stating that the EMF of the battery E is equal to 10 volt. The internal resistance is equal to 3 ohm and a current of 0.5 ampere is flowing in the circuit. So from here we can calculate that the EMF E minus I small r is equal to terminal voltage across the cell, and terminal voltage can also be written as I capital R, which is equal to E minus IR. So from this expression it is clear that we can calculate R in this way. I is 0.5, that is half, so R by 2 is equal to 10 minus 3 by 2, and from here we obtain that capital R is equal to 17 ohm. So if we calculate the terminal voltage of this battery, so terminal voltage, which is also equal to VA minus VB, is equal to I into capital R, which is equal to half of 17, and the value is equal to 8.5 volt. So the terminal voltage is equal to 8.5 volt and the external resistance is 17 ohm for this particular problem. Let us deal with the next problem. So the next problem is stating at room temperature, that is 27 degrees Celsius, the resistance of the heating element is 100 ohm. What is the temperature of the element if the resistance is found to be 117 ohm? Given that the temperature coefficient of the material of the resistor is 1.70 into 10 to the power minus 4 degrees Celsius minus 1. So if we consider this particular problem, so the reference temperature which the question is talking about is going to be 27 degrees Celsius, which is equal to 300 Kelvin. Now at this temperature, the resistance is 100 ohm. So we are calling it as R0, which is equal to 100 ohm. Now at a certain temperature, we are saying that the resistance measured is 117 ohm and the coefficient of resistance of the material is equal to 1.7 into 10 to the power minus 4 degree Celsius minus 1. So if we consider the equation that resistance at a temperature T above the reference temperature is equal to R naught 1 plus alpha delta T. So we can solve the problem for delta T over here. So if we put the values, we can calculate the temperature difference, that is T1 minus 27 or 300 Kelvin is equal to 117 minus 100, that is RT minus R naught, upon the value that is equal to the original resistance 100 into alpha, which is 1.710 to the power minus 4. So from here we obtain T1 minus 27 is equal to 1000, and I can say that T1 is equal to 1027 degrees Celsius. So at the temperature of 1027 degrees Celsius, the resistance of the element will become 117 ohm. Let us deal with the next problem. So that is stating that a negligible small current is passed through a wire of length 15 meter and uniform cross section 6 into 10 to the power minus 7 meter square, and its resistance is measured to be 5 ohm. What is the resistivity of the material at the temperature of the experiment? So we are asked to find out resistivity for this particular problem. So it is stating that the length of the wire is 15 meter and the cross sectional area is equal to 6.0 into 10 to the power minus 7 meter square. So they both are in SI unit and the resistance is observed to be 5 ohm. So if we use the expression R equals rho L upon A, so from here we can calculate the resistivity of the material, which is equal to resistivity is equal to RA by L. So if we put the values, we have 5 into 6 into 10 to the power minus 7 upon L, which is 15. So over here on solving we obtain 2 into 10 to the power minus 7 ohm meter. So this is going to be our answer for this particular problem. Let us deal with the next problem. So the next problem is stating the number density of free electrons in a copper conductor is estimated to be 8.5 into 10 to the power 28 per meter cube. How long does an electron take to drift from one end of a wire 3 meter long to its other end? The area of cross section of the wire is 2 into 10 to the power minus 6 meter square and it is carrying a current of 3 ampere. So for this particular problem, we begin in this way. The data which is given to us is equal to, so the number of free electrons, which is also referred to as the number of charge carrier, is equal to 8.5 into 10 to the power 28 per meter cube. And the question is asking us how long it is going to take for the electron to travel a distance of 3 meter, where the area of cross section is equal to 2 into 10 to the power minus 6 meter square and it is carrying a current equal to 3 ampere. So for this particular problem, we begin with our working formula. I is equal to NEAV, where V is regarded as drift velocity. So over here we can say that drift velocity is equal to length of the wire divided by the time it will take to cover that distance. So I can replace it in this way. I is equal to NEA. I equals NEA into the length of the wire divided by the time it will take to cover this distance. So from here I can say that the time it will be taking is equal to NEAL upon I. So if we put the values over here, we obtain 8.5 into 10 to the power 28 into electronic charge 1.6 10 to the power minus 19 into area, which is 2 into 10 to the power minus 6, multiplied by the length, which is 3, upon the current, which is again 3. So we can chop this out 3 and we will obtain the value of time, which is equal to 2.7 into 10 to the power 4 second. So this is going to be the answer for this particular problem. So post this, let us begin with understanding of Kirchhoff's law. So let us begin understanding the topic for today, which is Kirchhoff's law. Now it is a very interesting concept and will help us in problem solving of current electricity in the most efficient way. So Kirchhoff's law is also divided into two categories. We have a junction law and the another one is a loop law. So let us first of all begin with the junction law. So first we will state the junction law. So over here it is stating that the sum of all the currents directed towards a point in a circuit is equal to the sum of the current which is directed away from the point. So I can consider it in this way, that if suppose in a circuit there is a junction like this where the current from different branches are meeting. So I am calling this branch is carrying current I1. This branch is suppose carrying current I2, and then this branch is carrying current I3, and this one is carrying current I4. So the amount of current entering at a node or amount of current entering at the junction is equal to the amount of current which is leaving the junction, and hence from a very simple logic I can say that I1 plus I2 is going to be equal to I3 plus I4. So this statement is basically the junction law. Now junction law is also in accordance with the law of conservation of charge, because when we define current we say that it is defined as the rate of flow of charge. So if it takes place in the same interval of time, so I can say that the charge is conserved. So basically the charges which is entering at a point is equal to the amount of charges which is leaving the point. So it is also the statement of charge conservation. The next which we will be using is regarded as the loop law. So let us understand the loop rule or the loop law. The loop rule or the loop law. So it is basically stating the algebraic sum of all the potential differences along a closed loop in a circuit is 0. So it is just like applying Ohm's law a multiple number of times in a circuit. So let us understand it by applying it in a particular circuit. I am repeating the statement one more time. It is defined as the algebraic sum of all the potential differences along a closed loop in a circuit is 0. So we are considering a closed loop somewhat like this. So this is resistance R1, We are just taking a portion of the circuit where there are different resistors and the current division is already done in a certain way. This one is R2, R3, R4, this one is E1 and this one is E2. We are considering that the current in the circuit over here is I1, over here is I2, over here is I3, and we are considering that the current from here is in the downward direction, that is I4, somewhat like this. And we are naming the different points having different potential as this one is regarded as point A, B, C, D, E and F respectively. So the point which is acquiring different potential is named in a different way from A to F. So if we are going in a loop, so when I say that we are going in a loop, so we are considering that we are going in a loop like this. That is, I will move from point A to B, B to C, C to D, D to E, E to F, and then will be back from F to A. So if I apply potential difference equation at every point, so I can write it in this way: VA minus VB. I am leaving a blank for the time being. Then we will write VB minus VC. I am again leaving a blank. VC minus VD. VD minus VE. VE minus VF. And then we have VF minus VA. So if we apply Ohm's law a number of times in the circuit so that we can reach back to the original point, that is algebraic sum of all the potential differences along a closed loop in the circuit, so we are already getting the value equal to 0 on the left hand side. All these potential will cancel each other out. So if I start writing the values of potential difference, so from A to B, the current is in the direction from A to B, and hence the value is going to be positive, that is plus I1 R1. From B to C, again the current is in the direction from B to C and the value is positive, plus I2 R2. From C to D, the potential difference is going to be minus E1. Minus E1. So it must be very well kept in mind. Let me explain it over here. Suppose we are having a battery with a EMF E0, and this one is a point P and this one is a point Q. So if we will be writing Vp minus Vq, so the value is going to be plus E0, and when we write Vq minus Vp, the value is going to be minus E0. So this must be very well kept in mind. So over here we are writing for the next Vd minus Ve. Again we are in the direction of current, so it is plus I3 R3. For Ve and Vf, now we are going in the other direction of current, so we will be putting a negative sign, so it will become minus of I4 R4. So opposite to the direction of current, negative sign will be used. And then for writing Vf minus Va, we will put over here plus E2. So this is the way we apply Ohm's law for a multiple number of times in this entire circuit. And now if I do the addition, so we see that the algebraic sum, so minus Vb plus Vb cancel out, Vc minus Vc, Vd, Vd, Ve minus Ve, Vf, and then plus Va and minus Va will cancel out. So the algebraic sum of all the potential differences along a closed loop in a circuit is 0. So we are equating 0 as I1 R1 plus I2 R2 minus E1 plus I3 R3 minus I4 R4 plus E2. So this is the Kirchhoff's loop rule or loop law for this particular circuit. The loop law directly follows from the fact that the electrostatic work in a conservative force and the work done by it in any closed path is 0. So basically the loop law is in accordance with the law of conservation of energy. So the loop law or the loop rule is in accordance with the law of conservation of energy, whereas the junction law is in accordance with the law of conservation of charge. Now let us begin with grouping of batteries. So by applying Kirchhoff's law, we will find out an equivalent circuit by replacing batteries which are connected in series or parallel. So we are beginning with understanding of grouping of batteries. So for the grouping of batteries, the first we are dealing with is series combination of batteries. So in the series combination of battery, we are dealing with a battery having EMF E1 and internal resistance R1. Another one is E2 having internal resistance R2, and it is connected with an external resistor capital R. So we wish to write the current through this external resistance and find out the equivalent value of EMF. So over here this one is E1 having internal resistance R1, it is E2 having internal resistance R2, and we are considering that the current in the circuit is I. So the current in this circuit is I. So if we apply Kirchhoff's loop rule for this particular circuit, then we can write from here. So I am writing starting from here. So we will be going in this direction and we will coming back to this point. So if we write it in this sense, so we write it as I capital R plus I R2 minus E2 plus I small r1 minus E1 is equal to 0. And from here we can calculate the value of I is equal to E1 plus E2. So the value of current is calculated as E1 plus E2 upon capital R plus R1 plus R2. So I can say that whenever the two batteries having EMF E1 and E2 are connected in series such that their polarity are in order. When I say order, then I mean to say that this is the positive terminal, negative terminal, and the negative terminal is connected with the positive terminal of the another battery. So we can add the EMF of the two batteries, which will give us the equivalent EMF E0 upon R plus the internal resistance of the both the batteries, that is R1 plus R2, which can be written as R0. So I is equal to E0 upon R plus R0. So this is how the equation for the current will get modified when the batteries are in series combination. If the polarities of the batteries is reversed, then the equivalent EMF will become E1 minus E2, and we will take the mod value depending upon the which one is greater, E1 or E2. So we will take the mod value to obtain this equation. If we reverse the polarity, then we will write E1 minus E2 in the place of E0, but the value of internal resistance remains R0. So this one is for the parallel combination. if we understand, so sorry, that one was for the series combination. So let us discuss parallel combination. Parallel combination. So in case of parallel combination, the two batteries are connected in such a way that they will feed current into the same external circuit. So they are going to feed current in the same external circuit having resistance capital R. So this one is E1 having internal resistance R1. This one is E2 having internal resistance R2, and it is connected to an external resistance capital R. So we begin in this way, that the current which is flowing in this external circuit is equal to I, and I is the result of the two currents, that is I1, which is generated due to battery E1, and I2, which is generated due to battery E2. So this E1 and E2 will combine together to give us current I, and the current I at the end of the circuit will again distribute into I1 and I2 to reach the batteries E1 and E2 respectively. So if we consider this particular circuit, so if I apply loop rule, so for the first loop rule, I am containing the first battery, that is E1 R1, and the external resistance R. That is, I am doing something like this. I am taking the yellow loop. We are ignoring E2 R2. So if I write for this expression, so the expression will be IR plus I1 R1 minus E1 is equal to 0. So this becomes my first statement. So if we consider from here, so we are going in this direction, so positive I1 R1. Then over here again we are in the direction of current, so it is I1 small r1. We are hitting minus the negative terminal, so minus E1, and the value is equated to 0. In the second loop, I am selecting the second battery while ignoring the first one. So this time I can write it as I capital R plus I2 R2 minus E2 is equal to 0, which becomes my second equation over here. Now we are looking for the calculation of the total current. So the total current in the circuit I is equal to I1 plus I2. I is equal to I1 plus I2. This becomes my third equation. So if we solve the above equations, we will get the current equation in this form. So the current equation which we obtain by solving the above expression is equal to E1 R2 plus E2 R1 upon R1 plus R2 plus R1 R2. So this is going to be the expression which we obtain for current, and we can rearrange the expressions over here to get a look like this, that I is equal to E1 R2 plus E2 R1 upon R1 plus R2 upon capital R plus R1 R2 upon R1 plus R2. So this is a better way of representing our result. And then I can replace it with I is equal to E0 upon R plus R0. So the equivalent EMF will become E0, where E0 is equal to E1 R2 plus E2 R1 upon R1 plus R2. and the value of R0 will be equal to R1 R2 upon R1 plus R2. Again, the same thing must be noted that if in case we change the polarity of the battery, then the value of minus will be introduced in between the two terms. That is over here where we are using the positive sign. So it will be replaced with a negative sign in case if we change the polarity of the two batteries. So with this we have understood the grouping of batteries, and also the understanding of Kirchhoff's law is established.